Welcome to my class. My name is Dr. Fulkerson. This is Math Analysis for Business. It's also called Business Calculus because that's essentially what this is. This is calculus for business students. And today we're going to talk about the one concept that distinguishes calculus from everything prior to calculus, and that is the concept of a limit. So if you took trigonometry or algebra, you didn't talk about limits. But as soon as you're talking about limits, that's when you know you're doing calculus. So what is a limit? Well, let's begin by way of an example. Let's look at this function f of x equals x squared plus x minus 6 over x minus 2. And let's ask, what is f of 2? That's simple enough. Let's just plug in 2 everywhere we see an x. So f of 2 would be 2 squared plus 2 minus 6 over 2 minus 2. So notice in the numerator we get 4 plus 2, which is 6, minus 6, which is 0. And 2 minus 2 down here, we get 0. So our answer is 0 over 0, but what is 0 over 0? Okay, I thought anything divided by itself, like 3 divided by 3, wouldn't that be 1? But also, isn't 0 divided by anything? So like 0 divided by 7, isn't that 0? So which is it? Is 0 divided by 0, is it 0? Or is it 1? Or is it something else? Well, it turns out that 0 over 0 is undefined. Anytime you're dividing by 0 down here in the denominator, you're going to get something that's undefined. 0 over 0 is undefined. It's sometimes called an indeterminate form. And so what that really means is that 2 is not in the domain of our function. So f of 2 is undefined. But a question that we could still ask, though, is what if we plug in numbers that are close to 2? Like, what if we plugged in like 1.999 for x or 2.001 for x? What kind of output should we expect? And I want you to think about that. Just think about it. Maybe make a guess. What do you think would happen if we plugged in like 2.001 for x here, here, here? Plug it in. Do you think we get an output that's close to 1 or an output that's close to 0? Or maybe since if we're plugging in something close to 2, when we subtract 2, this will be close to 0. Maybe this thing is blowing up and getting bigger and bigger and bigger and blowing up to infinity. Well, it turns out that actually none of those things are the case. So I went ahead and made a table of values for this function. So I plugged in different values for x and found the outputs. And notice when we plug in 1.999, we got 4.999 as an output. Okay, when we plug in 2.001, we end up getting 5.001 as an output. Now, when we plug in 2, it's undefined, but notice that when we plug in numbers that are close to 2, but not equal to 2, we get outputs that are close to 5. So what we say is that the limit of this function, the limit of f of x, as x approaches 2, right, as that input approaches 2, is equal to 5. Okay, so this is the idea of a limit. And our notation here is we write the limit as x approaches 2, and this little arrow here is read approaches. So the limit as x approaches 2 of f of x is 5. Or you can write in the formula for the function here. Limit as x approaches 2 of this function is equal to 5. And there's different ways of saying it, but we can say as x approaches 2, that input approaches 2, our outputs, our f of x's, approach 5. And you can write it with the arrow notation as well. But this is the idea of a limit. Now, a question you might ask is, where does that 5 come from? That's very strange. It seems kind of counterintuitive that we would end up getting a 5 as an output. Well, we'll learn more about how you would compute a limit like this in the next video. This video is mainly about the concept of what is a limit, but let me give you kind of the idea here. So why did we get 5? Well, if we take our function f of x equals x squared plus x minus 6 over x minus 2, and if we try to simplify this function, what would happen? Well, by simplify, what I mean is we're going to factor the numerator. And it turns out the way that this factors is x minus 2 times x plus 3. If you work this out, x times x is x squared. We get a minus 2x from the inside two terms and a plus 3x from the outside two terms. So minus 2x and a plus 3x gives us a plus 1x. And minus 2 times plus 3 is minus 6. So notice it factors like this, and we can put the denominator in parentheses if we want. And notice that we can, if we cancel these x minus 2's or divide out these x minus 2's, we get x plus 3. But actually, I'm going to put a little question mark here. Is this really a true equality? Is this really equal to this? Okay, in fact, I could call this a function here. Let me give it a name, g of x. I could call this function g of x, and we have our original function f of x. And the question is f of x the same as g of x? Now, it's certainly true that this f of x is equal to this, and this is equal to this. But the question is this equal to this? Okay, in other words, for all values of x, are these the same? So are f and g the same? Well, it turns out for most inputs, they're going to be the same. So if you plug in like 10 for x, g of 10 would be 13. And if you plug in 10 here for x into f, so f of 10, turns out it would also be 13. Or if you plug in 0, g of 0 would be 3. And it turns out f of 0 is also 3. But there's one input where they differ. And that input is 2. Turns out g of 2 is 5, but f of 2 is undefined. Okay, f of 2, if you plug in fact, if you plug in 2 everywhere you see an x here, what do you get? Well, the denominator you get 0. The numerator you get 5 times 0, which is 0. And you can't really cancel those zeros, right? You just get 0 over 0, which is undefined. So these two functions are almost the same. In fact, the graph of this function is a straight line, right? It's a linear function of the form mx plus b, right? The y-intercept is 3, the slope is 1, so this is just a line. So the graph of this should also just be a line, other than when x is 2. And when x is 2, it should have a hole in the graph. In fact, I've graphed the function right here. This is our original function f of x, that kind of messy looking function here, this function right there. The graph is pretty simple. It's this, the function just x plus 3, right? We have a y-intercept of 3 and a slope of 1, but it has a hole in the graph there where 2 is. Okay, so notice that f of 2 was undefined, but if we plugged in values that were close to 2, we get outputs that are close to 5. Okay, so that maybe solves a little bit of the mystery about why we ended up getting 5 there as our result. Okay, so let's look at our informal definition of limit. We say f has limit L as x approaches c, and our L in the previous example was like our 5, and our c was like the 2. So we say the limit as x approaches c of f of x is L, if the values of f of x can be made as close as we like to L, to that 5, by taking the values of x sufficiently close to c, but not equal to c. Okay, and our c was 2. Or another way to state this, and I like to think of it this way, is we write this notation to mean if x gets close to c, but not equal to c, then the values of f of x get close to L. In fact, you can see that here. If our input values are close to 2, weren't those output values close to 5, right? If we plug in like 1.9, our output values are close to 5. And we can get our output values as close as we want to 5 as long as we take the input values to be sufficiently close to 2, but not equal to 2. Okay, so let's look at another example. And this one is maybe not quite as interesting, but it's pretty simple here. F of x equals x squared plus 1. And the question is, what's the limit as x approaches 3 of f of x? Now, is this the same as asking what is f of 3? And it turns out it's not the same thing. To ask what's the limit as x approaches 3 of f of x is not the same thing as asking what is f of 3. Now, in this problem, you're going to get the same answer, but it's not really the same question. Okay? The question is, if x gets close to 3 but not equal to 3, what does f of x get close to? So let's look at a graph of the function. So here we have a graph of the function x squared plus 1. And notice that if we plug in 3, we get an output here of 10. Right? That order pair 3 comma 10's on the graph. So f of 3 is 10. So, but the question is, though, what's the limit as x approaches 3? So if we plug in like 2.9, okay, what's our output going to be? Or if we plug in 3.1, what's our output going to be? Well, I made a little table of values here, and we plug in values that are close to 3, like 3.001. Turns out we get 10.006001. Or if we plug in 2.999, we get 9.994001. So notice that when we plug in values that are close to 3 but not equal to 3, we get values of f of x that are close to 10. Now, it turns out that f of 3 is also 10. Okay, but that actually has no bearing on what the limit is. It could be that we got 15 right here, and our limit would still be 10 as long as these values are getting close to 10 as we approach 3. Or this could even be undefined, and the limit would still be 10. So again, the limit does not depend on how the function is defined at that number, at 3, only how it's defined near the number. Right? As these inputs get close to 3, the outputs get close to 10. Okay, so we say that the limit is 10. So based on both the table and the graph, we can say that the limit as x approaches 3 of this function is 10. And in this example, we also had f of 3 being 10. So we have this limit as x approaches 3 of f of x ends up being the same as f of 3 in this example, but that's not always true. Is it always true that you can find the limit by just plugging in that number. You can find the limit as x approaches 3 of f by just plugging in the number. It turns out you can't. It's only true if f is what's called continuous at c. And we will talk about continuity a little bit later. Okay, so let's look at another example. Here we have a function that's a piecewise function, so it has two different formulas. So one formula if x is not equal to 1, another formula if x equals 1. So notice we could say, what's f of 1? Well, f of 1 would be 5. But then we could say, like, what's f of 9? Well, we have to ask ourselves, is 9 equal to 1 or is 9 not equal to 1? Well, 9's not equal to 1, so we have to plug in 9 here. If we plug in 9 here, we get 11. So f of 9 would be 11. Okay, now what does the graph of this look like? Well, the graph is mainly going to look like x plus 2, right? X plus 2 looks like this, right? It has a y-intercept of 2, slope of 1. But it's going to have a hole in it, right? Because when x is 1, it's not going to be defined to be 3 like we'd expect it to be. It's actually defined up here at 5. So the graph of this function looks like this. Now, what we could ask, though, is what is f of 1? Well, notice f of 1 is 5, right? Either based on this or based on the graph, we can see f of 1 is 5. What's the limit as x approaches 1? What if we plug in values that are close to 1? Like, okay, 0.9 or 1.00001. What are our output values going to be close to? Well, those output values are going to be close to 3. So this limit is equal to 3. Well, notice the limit as x approaches 1 of f of x was not the same thing as f of 1. Okay, f of 1 was 5. The limit, though, was 3. Okay, so these two things are not the same. They're not asking the same thing. This is asking how is the f defined at 1. This is asking how is f defined near 1, but not equal to 1. Okay, let's look at another example. And this one, I've called it f, but we don't have a formula for this function. And one thing you could ask about this is this really a function? Does it pass the vertical line test? And it turns out it does. Every vertical line you draw is only going to intersect this graph at most at one point, even this vertical line. It only intersects the graph there. It does not intersect the graph down there. There's a hole in the graph. Okay, so let's answer these questions. What's f of 1? Well, notice f of 1 is not way up here. F of 1 is actually just 3. Now, what's the limit as x approaches 1? Well, if we plug in these values that are close to 1, notice our output values are going to be close to 7. Okay, so their limit as x approaches 1 of f of x is 7. Now, what's f of negative 2? Now, nothing really all that interesting is happening at negative 2. Notice f of negative 2 is 1, but also the limit as x approaches negative 2 of f of x is also 1. So if we plug in something a little to the left of it, like negative 2.1 or negative 1.9, which would be a little to the right of it, notice our output values are close to 1. Okay, so here, the function is actually continuous, so we have the same value here for how f is defined at 2 and how it's defined near 2. Okay, now what is f of 4? Well, over here, f of 4 is 5. But what's the limit as x approaches 4? Now, you have to be a little careful here. So it kind of depends on whether we're on the left side of 4 or if we're on the right side of 4. Now, if we're plugging in a value that's a little bit less than 4, like 3.999, we're getting outputs that are close to 2. But if we plug in values that are a little bit bigger than 4, like 4.001, we're getting outputs that are close to 5. So we're not getting close to one particular number. We're kind of getting close to two different numbers. And so what we say here is that the limit does not exist. And the way we write this is DNE. The limit does not exist. Essentially, it's because, well, we're going to talk about what's called a left-hand limit and a right-hand limit. The left-hand limit is not the same as the right-hand limit. So I'll say what that means in just a second here. But notice as x approaches 4 from the left, right? If we're letting our x values approach 4 from the left, f of x approaches 2. But as x approaches 4 from the right, f of x approaches 5. Okay, since those values are not the same, since 2 and 5 are not the same, the limit does not exist. Okay, but what we can say is that it does have a left-hand limit and a right-hand limit. And the way that we write that is like this. Limit as x approaches 4 from the left. So this minus does not mean minus 4. We still have a positive 4 here, but it means that we're approaching 4 from the left. We're taking values a little less than 4, like 3.999. As we approach 4 from the left, the values of f approach 2. So the left-hand limit is 2, but the right-hand limit is 5. And we put a little plus here to indicate we're approaching 4 from the right. This doesn't mean plus 4. It is plus 4 here, but the plus here means we're approaching 4 from the right. Okay, as we approach 4 from the right, we got 5 as our limit. Okay, now the ordinary limit, the original type of limit that we were talking about, sometimes called the two-sided limit, exists if and only if both the left and right hand limits exist and have the same value. So now notice the left hand limit exists and the right hand limit exists, but they don't have the same value. So the ordinary original two-sided limit does not exist. Okay, let's look at one more function here. Let f be this function. Okay, what is f of 2? Well, notice f of 2 is down here at -1. Okay, what is the limit as x approaches 2 from the left? And again, this is positive 2, but we're approaching from the left. Well, as we approach 2 from the left, our outputs are really close to 3. They're approaching 3, so we get 3. As we approach 2 from the right, though, our outputs are approaching 6. And so what about the ordinary limit, the two-side limit? Well, again, this limit does not exist because the left and right-hand limits are not the same. Now, if these two had been the same, so let's say this had been 6 and 6, well, then the two-sided limit would exist. The ordinary limit would exist, and it would equal 6, even if this is still -1, or maybe even if this doesn't exist. As long as these two things are the same, the left and right-hand limits are the same, then the two-sided limit will be the same, okay, and that have that same value. Okay, now a question you could ask is, what if we have a function like this where it doesn't even have a formula? But the one thing that we know is that the limit as x approaches -2 from the right is 13, and also the limit as x approaches -2 from the left is 13. What can we say about the ordinary two-sided limit? Well, that would also be 13. Okay, because these two values both are 13. That would even be the case if f of -2 was some other value, so like 7, or maybe it didn't even exist. We would still get 13. All right, one question we could ask is it possible for left or right hand limits to not exist? Notice in this previous example that we did, even though the ordinary limit did not exist, we still had that the left and the right hand limits existed. So could we have a function that is weird enough that not even the left and right hand limits exist? And so I've gone into Desmos and I've graphed this function f of x equals 1 over x minus 3. And notice it has a vertical asymptote there at 3. So notice, in fact, I can even write it in as x equals 3, a vertical asymptote. Let me make it a dotted line here. So notice, what's the left and right hand limit as we approach 3? Well, as we approach 3 from the right, if we take inputs that are a little bit bigger than 3, so like 3.1 or 3.01, notice we're getting huge outputs. We're getting outputs that blow up to infinity here. So as we approach 3 from the right, the limit does not exist because it's blowing up. In fact, later we'll talk about infinite limits, and it turns out as we approach 3 from the right, this limit is infinity. Now, the limit doesn't exist. Just because we say it has an infinite limit doesn't mean the limit exists. The limit doesn't exist, but the reason it doesn't exist is because it's blowing up to infinity. Okay, and as we approach 3 from the left, if we plug in numbers a little less than 3, it's going down to negative infinity down here. Okay, so the limit as x approaches 3 from the left is going to end up being negative infinity, but it doesn't exist. So here's one way that a limit couldn't exist, at a left or right hand limit couldn't exist at a number. Another way is if we take a function like this, sine of 1 over x. Now, you may or may not have seen the sine function before. It's a trigonometric function, but sine of x is kind of a weird function, or sine of x is actually not too weird, but sine of 1 over x is a really weird function. Sine of 1 over x looks like this. Notice it actually oscillates back and forth infinitely many times in here. You can keep zooming in. It just oscillates infinitely many times. So it's kind of impossible to draw this by hand, really. But what's the limit as x approaches 0 from the right? So 0 is right here. As we approach 0 from the right, well, notice it's not blowing up. Okay, but the limit doesn't exist. The reason it doesn't exist, though, isn't because it blows up to infinity. It's because it's oscillating back and forth so that it doesn't approach one particular number as we get closer and closer to 0. And same thing with the left-hand limit. The left-hand limit will also not exist as we approach 0. So there's a few different ways that limits cannot exist. Left and right-hand limits cannot exist as you approach a particular number. Okay, so you might wonder, what do limits have anything to do with the real world? This all seems well and good for these functions that we see on paper, but what does this have anything to do with reality? So let me give you an example. So earlier today, I was driving in my Bentley on the highway. And by the way, I'm just kidding. I don't have a Bentley. But I was driving in my Bentley on the highway. You can just go with this. And I was trying to figure out, okay, how fast am I going? So I looked down at my speedometer and I noticed, oh, it doesn't have a speedometer in this car. Apparently, it's a very cheap Bentley. But I realized, though, oh, I can figure out how fast I'm going right now because I know that over the last 2 hours, I've driven 140 miles. So that means I'm going 70 miles per hour. But then I thought, well, wait a second. That doesn't tell me how fast I'm going right now. That just tells me my average speed, my average velocity over the last 2 hours. If I've driven 140 miles in 2 hours, that means I've averaged 70 miles per hour. But I could have been speeding down, slowing up. Of course, I know I was going faster than that at certain times, slower than that at certain times. There's always some guy in the left lane, some idiot driving 53 miles an hour in the left lane. And I know I wasn't going exactly 70 the whole time. So how can I figure out how fast I'm going right now? Well, then I thought, okay, well, maybe if I look at the last 1 minute instead of the last 2 hours, and I know how far I've traveled in the last 1 minute, I could figure out how fast I'm going right now, however many miles I went and so forth, and divide that out. But the problem is, again, that only gives me my average velocity over the last minute. If I want to figure out how fast I'm going right now, how do I do it? Well, I could look at the last 1 second. Surely that would tell me how fast I'm going right now at this instant. But again, you have the same problem. I could have been slamming on my brakes or speeding up in that 1 second time interval there. So that only gives me my average velocity. So you might think, well, why don't I just take the last 0 seconds? But the problem is the last 0 seconds, I've traveled 0 miles or 0 feet or 0 inches, however you want to talk about it. So if I actually try to figure out how fast I'm going based on the last 0 seconds, I would have to divide 0 by 0. And of course, that's undefined, just like we had our function earlier where we were dividing 0 by 0, and that didn't make sense. So you can't figure out your velocity by looking at the last 0 seconds, but you also can't figure out how fast you're going right now looking at the last 2 hours or the last 1 minute or the last 1 second or even 0.001 seconds. So how do you figure out how fast you're going right now? Well, you need to use a limit. You take the limit as the amount of time approaches 0. And then you look at your distances that you've traveled in those times, and those distances will also approach 0, but that ratio of the distance over the time, and you take the limit as that time goes to 0, that will give you your instantaneous speed, your speed right now. So anytime you're talking about a rate of change, like a speed, or a rate of change really of anything, limits are involved. Okay, so limits actually are important and valuable in real life situations.